Hello children, welcome back to my channel. Today we will be starting an important topic of laws of motion. Up till now we have spoken about motion along a straight line, motion in a plane. We have also dealt with the accelerated motion, how acceleration affects the motion, how the velocities change, and we have, based on that, we have derived many equations of kinematics, be it for motion in a straight line or along a plane. We have spoken about projectile motion, we have also spoken about uniform circular motion. Now, one natural question must have arisen in your minds, and that is, what causes motion? Or what causes acceleration? Why some objects move, some others don't? All these questions will be answered in this particular chapter. Now, first and foremost, what causes motion or what causes change of motion? That is, what causes acceleration in a body? And that particular thing is known as force. So what we have observed is that if there is an object, say a ball, at a stationary position, if we push it from one direction, it will move, it will start moving. So an acceleration will be imparted to it and it will start moving. Or alternately, if we take the same ball or some other object and pull it, then also it will start moving. So force is nothing but a push or a pull. That changes or tends to change the state of motion of an object. Say the ball was stationary, we pushed the ball, it started moving, or it was stationary, we pulled it, started moving. However, just because of the fact that we have pulled something or pushed something, it might or might not move. For example, if I push the blackboard or push the board here, I am applying a force, or I am pushing the board. However, the board is not moving. My intention is to move it. So force is an agency that changes or tends to change. That is, tries to change the state of motion of an object. Right? Now, that is not all the effects of force. If I apply force on an object, say we have a balloon, and if I squeeze it from all sides, apply or push it from both sides, what will happen? Its shape will change. Or if you take a rubber band and pull it, it will stretch, or its shape will change, its size will change. So this push or pull or force has three effects. It can either change or tend to change the motion. Now, when we talk about motion or state of motion, we say if the object was at rest, applying force might change its state of rest and it might start moving. If the object was moving, it might accelerate or decelerate or retard the motion. Further, as we have seen in the circular motion, application of force might simply change the direction. Because if the acceleration is perpendicular to the direction of motion, the path will be changed, however, the speed doesn't change. So, force can change, set a body at rest into motion. A moving body can be accelerated or retarded, and for a moving body itself, it can also change the direction of motion. So, basically what is happening is that, what is rest? Rest means velocity equals to 0, right? So what force basically does is that it changes velocity. Okay, further, force can also change the shape or size of an object. We can squeeze the balloon, or we can stretch the elastic band or rubber band, right? So these are the effects of force. Now in laws of motion, since the topic itself says it's about motion, so the aspect of force that we'll be discussing is how it changes the velocity. So now let's go back in history, say nearly 2500 years back, when science, philosophy, astronomy were thriving in ancient Greece. The great Greek philosopher Aristotle, he observed the basic things that we observe today also. We see that in general an object seems to be at rest. To set it in motion, we have to apply force. And if we apply force to an object, it will start moving, but after some time it will stop. So to keep the object in motion, what we need to do, we need to keep applying the force, which means that force, external force, you have to apply force from outside to keep a body moving. This was the law of motion given by Aristotle nearly 2500 years back. However, nowadays this is known as Aristotle's fallacy. Why? Well, for that we have to move fast forward in history to 17th century, that is nearly 1500 years later. Great Galileo Galilei, he performed certain experiments to see or to establish whether Aristotle's law was correct or not. Now what he observed, first experiment, what he did is he took an inclined plane, okay, and released an object or a ball from the top of it. What he observed is that as he released it, the object starts accelerating or gathered speed. Or we can say that acceleration takes place. He performed the same experiment with another incline. Now what he did is that he set an object moving and rolling towards the incline and allowed the object to move up the incline. As the object started moving up the incline, he saw that it lost speed. That is, there was a retardation. So, what is the natural conclusion of these two experiments? By the way, this is known as Aristotle's experiment with a single incline. What it means shows is that a downward slope, if an object moves down a slope, it will accelerate. If it moves up a slope, then it will decelerate. So he concluded, or he inferred from this, that if an object is allowed to move in a horizontal plane, no incline up or down, then it will keep on moving till it goes to infinity with a constant speed and in a straight line. This was a revelation. This was complete contradiction to Aristotle's law of motion that was prevalent at that point of time, that external force is required to keep a body moving. Galileo found that actually if the object is moving, then there is no external force required to keep it moving. On the contrary, it will need external force to stop the object. Now, after performing this experiment, Galileo performed a further experiment. In this case, what he did is that he took two different inclines instead of a single incline. So, he allowed the object to move down the incline, one incline, and then put another incline here, and tried to measure how far up the incline it will go. So the object moves down this, goes along this path, and then moves up. And what he found is that the object will move approximately to the same height as it started. Almost the same height as it started. Now what he did is that he took another incline, another setup, where first incline was the same, say, and the height from which the object was released was the same. However, he made the slant much more, the angle much more smaller here, this angle. So the incline was little less steep than the previous one. Now what he observed is that even in this case, when the object moves down the incline and keeps on moving in the path, it will keep on moving till it reaches the same height again. So what he concluded is that if it kept on decreasing this particular angle and making the incline less and less steep, so that ultimately he reaches at a condition where the object moves here and the incline is along the horizontally now. The angle, this angle becomes 0. Then, by tendency of the object, it will keep on moving till it reaches this height. But this height will not be reached ever, because it's a horizontal plane. So the object will keep on moving till infinite distance. So these two experiments led Galileo to conclude that a body which is moving with a certain speed along a straight line will continue its motion along the same straight line until and unless an external force stops it or causes it to change its state of motion. What it means? See, if the object is moving at certain speed along a straight line, let us say we take this object, a ball, and it's moving with certain speed v along a straight line. So it is basically a uniform motion, or we call this, since it's in a straight line, its velocity remains the same. Now, it will keep on moving till infinity if there is no external force that causes it to change its velocity, its magnitude, or in its direction. Now, if we go back to Aristotle's equation or Aristotle's law of motion, what he found is that the objects, after moving certain distance, start slowing down and it stops. Why it happens? The answer to this is that when you allow an object to move on the earth, what happens is moving over some other surface, and when it's moving over the surface of resisting force known as the friction, which we will discuss at a later point of time, at a later video, and also some resistance comes from the air also. As a result, result of these resistive forces, the object slows down and ultimately stops. If these two things were absent, if friction was not there and if there was no air resistance, the object would have moved on till infinity. Okay. So this is the new law of motion. as propounded by Galileo, that in the absence of external force, an object in motion will keep on moving with uniform speed along a straight line. Okay. So it means that there is an inherent tendency of an object to keep on moving. Now remember, if the object was at rest, then the object will remain at rest, because we need some force to set it in motion. So there is an inherent property of objects whereby, number one, whereby it resists any change to its state of rest or its state of uniform motion along a straight line. This inherent property, by virtue of which an object resists any change to its state of motion, that is any change to its velocity. We have already said that state of rest is defined by velocity v equal to 0, and uniform motion along a straight line, its velocity v will remain same, so it will not change. This inherent property of an object to resist any change to its state of rest or its state of uniform motion, this is known as inertia. So law of inertia is one of the greatest contribution of Galileo to physics. Okay, now we have defined inertia as the inherent property of an object to resist any state of its rest or motion along a straight line. So inertia can be divided into two parts: inertia of rest and inertia of motion. Inertia of motion can be further divided into inertia of speed, that is, the speed remains constant until and unless an external force changes it, or the direction in which the object was moving will remain constant until and unless a force makes it to change the direction. Either which case, both the cases, velocity will change. So inertia of motion is inertia of velocity basically. Inertia of rest is also inertia of velocity. Now coming back to our basic observations, what we have seen is that if you take a less massive object, say the tennis ball. So a tennis ball, if it moves with certain velocity, say v, or if we apply certain force to it given by F, then it will start moving with a velocity v. Same thing if we take a basketball and apply the same force to it, will it move with the same velocity? No, right? It will move with certain different velocity, which means that the opposition or resistance to change of motion of the object, motion by the tennis ball given to the force F is smaller compared with the resistance given by the basketball. Why it is so? Because the basketball has a larger mass compared with the tennis ball. So mass is something that determines inertia. If the object is more massive, then it will be having more inertia. In other words, mass can be said to be a measure of inertia. Mass is of inertia. This is because of that particular inertia that even if I push this board attached to the wall, I cannot move it because it is much more massive and my force is negligible compared with the resistance it's providing. Okay. Now, let us say both these two objects, the tennis ball and the basketball, are two masses, small m and capital M, where capital M is larger than small m. Mass m is greater than small m. Both are moving with the same velocity v. If both the objects are moving with the same velocity, then equations of kinematics or the previous chapters we will not be able to differentiate between the motion of the two. However, we know one thing: the tennis ball or the smaller mass, if it's moving towards you with a velocity, certain velocity, it's easier to stop, or it will show less amount of inertia or less amount of motion compared with the larger mass moving with the same velocity, which in other words means that the entire motion of an object is not only the velocity but also the mass included. So we define a term momentum, which gives us a measure of the entire motion of the object, which means the resistance we require or the inertia of the object, the amount of force or amount of effort we require to stop the object or put the object into motion with certain velocity. And this particular term momentum mathematically is defined by, given by the symbol small v, is equal to the product of mass of the object and the velocity with which it's moving. Since we are saying velocity, so it will be a vector, and so momentum scalar multiplied by vector will be a vector quantity. This term momentum is going to be very important in the coming discussions. So momentum is mathematically the product of mass and velocity of the object, and it's nothing but a measure of the amount of motion that is carried by the object. Now, if you look at this equation, we can say that the dimensions of momentum will be dimension of mass multiplied by dimension of velocity, and its unit will be in SI. Mass is kg, then meter per second, and in CGS unit it will be gram centimeter per second. Okay, so this term momentum or this equation is one of the fundamental equations that we will require when we go into the Newtonian physics, or we enter the realm of Newton's laws of motion. Now, let us consider, prior to going into Newton's laws of motion, let's consider this equation P equal to mv. Now, if we consider here that m is a constant, m doesn't change. That is to say, if m is a constant, then we can say that P is equal to, P is proportional to V. Why? Because m is constant and it can be treated as a constant of proportionality. In that case, if I plot P into y-axis and V in the x-axis, P proportional to V means it will be a straight line moving through the origin, right? Again, in the same equation, if I consider V to be constant now, in that case, P will be proportional to m. What it means is that for the same velocity as we have discussed, more the mass, more will be the momentum. So the plot of P along y-axis versus V along x-axis will be again a straight line passing through the origin. Now, if I consider momentum to be constant, that is to say, P is constant, in that case, what we have that m is proportional to 1 by v, or mv is equal to constant, which will mean that v is proportional to 1 by m. And so if I plot a graph between v and m, then it will be c. For smaller m, we need larger v. For larger m, we need smaller v to have the same momentum, to keep p constant. So we will have a graph like this. Okay. As the mass increases, for lesser velocity, we will have the same constant momentum. Okay. In the 18th century, Sir Isaac Newton came, and he finally completed the unfinished work of Galileo Galilei. Galileo couldn't finish his work. He found the laws of inertia. He found that force is not required to keep the object in motion. If it is in motion, it will keep on moving. Based on Galileo's observation, and Newton came up with, and also his own inputs, Newton came up with 3 laws of motion, which actually gives us the name of the chapter, laws of motion. Now, the first law, or Newton's first law of motion, states simply that an object cannot change its state of motion on its own. In other words, every object will continue its state of rest or of uniform motion along a straight line until and unless it is compelled by an external force. Please note the term external. So, if there is an object which was initially at rest, it will not start moving spontaneously on its own. Or if there is an object which was moving along a straight line which has constant speed, it will not increase or decrease its speed, or will not change its direction of motion on its own. To do so, we need to apply a force from outside. An external force is required, right? This is first law of motion as given by Newton. Now, it simply means that if there is no external force, say we call external force equals to 0, we are not applying any force, then what will happen? Then the object will continue its state of rest and of uniform motion, as its tendency is, as given by law of inertia. So, Newton's first law of motion is nothing but the law of inertia, stated in a different way, by incorporating or emphasizing the importance of external force. Okay, now about the second law of motion, as propounded by Newton. So, what he saw or what he observed is that if we apply a force from outside, an external force is applied to an object or a body, its velocity changes. If the velocity changes, we know that even if the mass is constant, change of velocity will mean the change of momentum. So what he found is that the external force actually changes the momentum, and by how much or but at what rate it changes is directly proportional to the external force or the magnitude of the external force. So what it means is that, or what it states, the second law of motion simply states that the rate of change of momentum of an object is directly proportional to the applied unbalanced external force, and the change takes place in the direction of the force. So what it means is that, let's say we have an object of mass m moving with certain velocity, say v, so say u, and it's acted upon by a force external, and its velocity now becomes v. So its initial momentum was mu and final momentum is mv. So mv minus mu has taken place over certain amount of time, which will be t. So mv minus mu by t, that is rate of change of momentum, is proportional to F external. And also the velocity of the object was in this direction, say, and after applying the force, the change of velocity is also taking place in the direction of the applied force. Now, this is what we learned from class 9 also. In class 11, what we will be doing is that, since we know the basics of calculus, so we know that in case of instantaneous cases, dp by dt will give us the rate of change of momentum, and by Newton's second law of motion, this dp by dt has to be proportional to the applied force, applied unbalanced force. Now, what do we mean by unbalanced force? Unbalanced force is that force which, say, it's not necessary that there is only one external force. There could be different amounts of forces. For example, the object is there, so there will be force of gravity always, and then there will be a normal reaction from the surface on which it's standing. These two forces are external forces to the object. However, these two forces are equal to each other and they balance each other out. So this will not change the state of motion of the object. The third force that we apply, Fext, from some other direction, is responsible for the change of momentum. So unbalanced force means even if there are multiple forces acting on it, the net force, or if they do not cancel each other, the resultant of the force, all the forces, is the unbalanced external force, and that particular force causes the acceleration of the object. We will stop the video for today here. This will be our starting point for the next video, where we will discuss the second law of motion and then see certain implications or applications of this second law. Thank you.